Hi, Al Williams here with Hackaday. We're finally ready to take our Verilog design and put it onto the Lattice iCEstick FPGA board. We're going to use a couple of open source tools to do that, most notably IceStorm, which actually is the software that will program the bit stream. That's the configuration file we're going to generate onto the board. It also provides some databases for another open source tool called Arachne, which is the place and route tool. And the place and route tool needs to have some digested Verilog, and that's going to be the job of another open source tool called IceStorm. So we're going to use those tools in concert. The instructions for setting all that up are on the IceStorm page, which you can get to with the article that goes with this video. And you really need to install the latest versions of that following the instructions there. If you use like Ubuntu and you've got a repository, it may have a version of these tools in there. They may not be up to date enough to get the job done. So I asked the question last time, what happens when you've got your Verilog code and you've got things like clock, LED1, PMOD1, how do those get mapped into the actual pins on the FPGA? And that's a good question. The names here are suggestive of what pins they should go to, but it turns out these tools don't have any way to know what those names mean. So somehow I have to define that clock goes to a particular pin and LED1 goes to a particular pin. And the way we do this, you have to understand a little bit about how your Verilog gets sent down to the chip. When you use IceStorm, it's going to take your Verilog and kind of decompose it into very basic logic functions. And those basic logic functions will get mapped into particular places on the FPGA. And there's different types of resources that it might map. So there's logic blocks, there's I/O pins, there's memory, there's a few other things like that. Well, the I/O pins are the ones we're really worried about here. If we just let the place and route tool randomly assign I/O pins to things, that's not going to work on our PC board. And in particular, if I tried to drive an output on a pin that was already connected, say, directly to ground or directly to power, I could potentially short something out and burn up my FPGA, which for a $22 FPGA board isn't the worst thing in the world, but a lot of FPGAs are a lot more expensive than $22. So you generally don't want to do that. The way we're going to do that is we're going to constrain the place and route tool. And that's not the only kind of constraint you'll run into with an FPGA development system, but it's the only one we're going to talk about today. But the idea is while it's doing all this placement and all the routing, we can give it certain guidelines and say you have to do this or you have to take this into account. And in our case, we're only going to say you have to put this named signal, like clock or LED1, into this particular I/O location. And the way we do that with this tool set is we build a PCF file, which is just a text file. And I've already made one called iCEstick.pcf. It's got all the different pins that these boards have on them. So there's the clock, there's LED1, and the syntax is very simple, right? Set I/O, LED1 99. That means use pin 99 for LED1. The Arachne tool, the original version of it, didn't allow you to have an unused constraint in here. And so if you look, I've got everything that I'm not using in this project commented out with the double comment marks. And that allows me to very easily go in on a new project and uncomment the things I want to use and comment out the things I'm not using anymore. And I can get that to work. The latest version of Arachne, I actually asked for it on GitHub, was to change it so that we could actually leave these all in here all at one time, and the author graciously put in a special syntax that you can mark a line as it's okay if this one's not actually in the design. I haven't updated the PCF file to accommodate that yet, but be aware that you could do that now. But for right now, I've just left it like this so that we only have the lines uncommented that we're actually using in the design. So that's going to constrain the place and route, and it'll allow the I/O pins that we talk about in the Verilog file to go to the right pins on the FPGA. Very important. The other thing that was important, this is just the file we had last time in simulation, but remember I had changed a couple of things in the counters. I had changed the count to go up more quickly for simulation, and I changed that 91 to a smaller number so that it would simulate faster. Well, of course, we're going down to a 12 megahertz part now, we actually need it to count by 1 and check for 91. So make sure you've got those changes in your code. I've got those in a file called demo.v. So I mentioned the first thing is we've got to get the synthesis, and we're going to use Yosys for that. And Yosys takes a command syntax like this. We tell it we're going to use the ICE40 synthesizer. Our output's going to be a BLIF file. You don't really have to worry about what a BLIF file is. We'll look at it in a second, but it's going to be the decomposed logic of your Verilog file. And so we'll just call it demo.blif. And then it needs to know the Verilog file, so I'm going to say demo.v. If you had a complex design where you had more Verilog files, you'd add them here. So, you know, if I had library.v or something, I could put that here as well. In this case, this is all I've got, so that's fine. And a lot of information here. You can see it comes out and tells you some statistics about your design, how many processes, how many cells, what kinds of cells it's using. If you go dig into the data sheet of the FPGA, all that has meaning, and if you really are trying to optimize something, you can take a look at that. It's about like writing in C and digging down into the assembly. You can do it, you frequently don't have to do it. So for right now, I'm going to fixate on found and reported 0 problems. That's a good sign. And just for fun, let's look at the BLIF file. There'll be some things here that you recognize out of your design, you know, your inputs, your outputs, but then you're going to see a lot of things about gates and attributes and LUT parameters. LUT's a lookup table. That's one of the core pieces of the FPGA in this particular FPGA. So, you know, not something you really want to read through and try to understand unless you're trying to do something special, but that data's there. So the next thing we've got to do is we've got to take all those basic logic functions in the BLIF file, and we've got to get them allocated into very specific places in the FPGA and tell the FPGA that we want to connect certain ones together. And so almost like auto-routing a PC board in a sense. So to do that, we'll use the place and route tool called Arachne. And it's actually Arachne PNR. The device type is the 1K. And here's where our constraint file comes in, iCEstick.pcf. So that's the file that connects the pin numbers to the Verilog net names. And then we're going to do demo.blif. That's the file we looked at with the basic logic description in it. And we need an output, so I'll do that as demo.txt. The output of this tool is an ASCII text file. You can read it, but the tool that programs the FPGA can't read it. So we'll have to do another step to convert it into a binary bit stream. And that was relatively quick. It did in fact tell us some statistics. We're using 9 I/O blocks and 13 logic blocks out of 160, and we're not using any memory out of the 16 memory blocks that are available on the chip. So you can kind of get an idea of how full you're getting your chip when you run this step. And I'll take a look at demo.txt, but generally you don't care. This is the various configuration bits, and it's all very well documented by the IceStorm project, by the way, as to what all this means if you really want to dig into it. But practically, you can kind of treat this as a black box. Like I said, the text file doesn't do us any good unless I convert it to binary. So IceStorm gives us a tool called IcePack, and we'll tell it demo text, and we want out the bit stream, which is going to be demo.bin. I'm not going to show you the binary file. You could dump it with OD or something, but it's totally meaningless. It's a representation of what we saw in the text file. And what will read it, though, and do something useful with it is iceprog. And that's going to go find the iCEstick based on the USB ID, so it doesn't need to be plugged in. I've had some trouble using it through certain hubs. So if you have trouble and you're sure it's there, you might try putting it into a different USB slot. And as you can see, it takes a few seconds and it programs the EEPROM on board. And then if you look at the actual device running, it's executing the Verilog that we gave it. Now keep in mind, just like we said in the first part, it's not really executing the Verilog. The Verilog described the circuits and described the interconnections, And all this process has done is mapped that into the primitive circuit elements that the FPGA has on board, and then did that configuration. So even though it's pretty common to hear people say it's executing Verilog, that's very misleading to people who don't understand the process, because it sounds like it's actually running a program, and that's just not the case. So let's look at it live here for a second. Here's the actual iCEstick on a breadboard. I'm using a USB hub just to power it, and I soldered some headers on the side for power and ground. The inputs are up through the PMOD connector on the top. There's no PC, but the configuration flash right about here is holding the FPGA's configuration. You can see I have a reset button on the bottom, and the A and B buttons are up near the top. The switches are connected to 3.3 volts, and I put some pull-down resistors to ground. The value of the resistor is not very critical, but without them it takes a little while for the floating input pins to discharge after you let go of a switch. Apparently there's no onboard pull-ups or pull-downs on the board. You can see the LEDs are already blinking because of the multi-stage timer we built in Verilog, and that looks to be about a half a second. So the thing we really want to test is the adder. And for that we're going to go to the buttons up at the top, the A and the B button. And when you set one of those buttons on, that's going to put a 1 on the device, and the sum of 1 and 0 is going to be a 1, so that LED lights up. D1 down there at the bottom is the sum. Now if I go to the other input, now I've got 0 plus 1, which is still 1, so I get the same result. If I put both bits to 1, I'm going to get a carry of 1, which is D2. The sum is 0, and I also light up that top LED. That's the carry latch. That's the latch part that remembers that a carry happened. So even after I take my fingers off, that LED stays lit now, and it'll stay lit until I go over and hit the reset button near the bottom of the board. There it is, it went off. So that pretty much works the way we expect. 1 plus 0 is 1. 0 plus 1 is 1. Both of them come on. That's a 0 with a carry, and the carry's latched. It all works. And so that about wraps this up. We took a Verilog design. It had some combinatorial logic. It had some sequential logic. We synthesized it. We did a place and route step on it. We created a bit stream, and we loaded it down into the board. We also simulated the Verilog, so we were pretty sure it would work when it went onto the chip, and it did. So, granted, this is about the simplest FPGA project you could imagine. And to do anything really practical, and especially anything that's actually useful to do on an FPGA instead of on a microprocessor, it's going to be a lot more complicated than this. This has just scratched the surface, but my experience has been sometimes getting over that first speed bump when you're trying to learn something new is really what stops you. And my goal here was to kind of get you over that one speed bump. There's a lot of resources on the web. We talk about FPGAs quite a bit on Hackaday. Hopefully this will get you started, and you'll follow along from there. I appreciate you watching and hope you enjoyed this whole series. Thanks a lot.